So welcome everybody to the second lecture. So Luis, please go ahead. Yeah.
Yes. So in the lecture of yesterday, we had a look to the very basis of Bose-Einstein condensation. So we started with the Bose-Einstein condensation in ideal Bose gases, then an idea of critical temperature, the idea of off-diagonal long-range order, how it relates with condensate. We introduced interactions and introduced the concept of scattering length and repulsive and attractive interactions that we were discussing also yesterday. And then we started the discussion about the interacting Bose gas in free space. So we introduced the Bogoliubov approximation, so basically approximating the creation and annihilation operators in the condensate by a C number. And then we obtain the quasi-particles and the quasi-particle spectrum, which describes the excitations in the condensate. And in particular, we had a look to this spectrum, which is the so-called Bogoliubov spectrum, and which consequences this has, in particular, for the idea of superfluidity. So, yesterday, all the discussion that we were having was in the context of Bose gases in free space, so without confinement. And therefore, the condensate had an uniform density. However, in experiments, the Bose-Einstein condensate is, of course, confined. Yes, there is a trap. Atoms are trapped by optical means, so by lasers, or by magnetic means, or by a combination of them. And therefore, the BEC is not spatially uniform. So we would like to discuss today what happens in that case, yes, and which is the equation that describes actually the condensate. But before going to that, let's introduce the idea of what is called the condensate wave function. So for this, we should remember the idea that we were discussing yesterday about the density matrix, single particle density matrix. Yes, so psi.
Yeah, sir, just can you just very briefly summarize yesterday's lecture? That will be helpful.
I already did.
Oh, sorry, I joined late. Okay, fine.
Okay. So as I said, the lecture of yesterday was about condensate in uniform space. You can repeat just very briefly. Condensate in uniform space. So we introduced the idea of Bose-Einstein condensation in ideal gases, the idea of off-diagonal range order. We introduce interactions, sorry. And then we discuss the theory for a weakly interacting Bose gas in free space, and in particular, the idea of quasi-particles and the corresponding spectrum of quasi-particles, which is the Bogoliubov spectrum. And then we show that it has this phonon branch and this quadratic branch, this single particle branch. And due to the presence of this phonon part of the spectrum, this linear part of the spectrum and small momentum, then we saw a direct connection to the idea of superfluidity through the idea of what is called the Landau criterion. So today we want to have a look to what happens if the BEC is trapped, and for this, let's introduce first the idea of condensate wave function. Yes, so this was the single particle density matrix. Yeah. And the single particle density matrix, we can diagonalize this matrix, and then we get something like this. Yesterday, when we were discussing a non-interacting gas, these were the single particle wave functions, the single particle eigenstates. Now here there will be some states which diagonalize this single particle density matrix, and these are actually called the natural states in the literature. Natural states. Natural states. So let's now expand the field operator in these spaces of natural states. These are the creation of, in this case, annihilation operator for particles in the natural state I. So then I can then rewrite this Hamiltonian, this density matrix, sorry, as this sum and this, of course, is just Ni delta Ij. Yeah? So I have introduced these creation and annihilation operators for the particles in these natural states. And yesterday we said that if a temperature is smaller than the critical temperature, then I have a condensate. And this means that one of these natural states will be macroscopically occupied. Yes, let's say the natural state 0 is macroscopically occupied. So this one of these Ni's here will be macroscopically occupied. So this will be of the order of the total number of particles. And this means that the corresponding wave function phi0 of R, yes, will play a very important role. Yes. This will actually be the condensate wave function. Yes. So now this means that we can write psi R. We can take first this contribution of the 0 mode, of the condensate mode, plus the rest. Yes, plus the rest. Now, I can, for a temperature much smaller than the critical temperature, then, as we said yesterday, I can take this as C number and 0. So then I can write my operator in two parts. One part, which will be this part, which is what I will call psi 0, which is what I will call the wave function of the condensate, which is square root of n0 phi 0 of R. This is the wave function of the condensate. The condensate wave function. And then there will be this part of here, which will be the rest, yes, which will act as quantum fluctuations on top of the, or fluctuations on top of the condensate wave function. So this condensate wave function, yes, plays actually a very important role. And as it was mentioned yesterday already, this condensate wave function is as a complex number, actually. It has both an amplitude and, very crucially, a phase. Yes. So, of course, psi 0 R square will give me the density of the condensate, and SR, as I say, is the phase. And the phase plays a very important role. Actually, this phase is defined up to a constant. Yeah, so I could add here any constant, alpha, let's say, and I will get exactly the same. So this is actually a gauge symmetry in this problem. And this gauge symmetry is actually spontaneously broken when choosing a particular phase of the condensate. So in any realization, it is spontaneously broken. Okay, so actually this condensate wave function acts like an order parameter that characterizes the BEC phase. So for temperature larger than the critical temperature, this is also an order parameter. Because for temperatures larger than the critical temperature, I don't have a condensate. For temperature smaller than the critical temperature, this N0 is of the order of, this square root of N0 is of the order of N. So it starts to grow, so to say. So this condensate wave function is indeed and plays the role of an order parameter for the BEC transition. Okay, this is the first thing I wanted to mention, this idea of condensate wave function. Now, other thing which is interesting is that this actually is psi, as I say, we have written CR as a C number plus a fluctuation here. Now, I can understand this psi 0 actually as the mean field, actually the average value of this operator. This is called mean field. Yes. Okay. And but we should understand actually what this mean field actually means. Yes. And this is important for the following reason. As I was commented to you, this psi, this psi r has two parts, this C0 r A0 plus the rest, plus this delta phi. Now, if I have a look to this, this number of here, so if I forget about this term here, and I just approximate this into that, and I take this psi r, then you can see that actually this A0 is destroying particles. Yes. So the way of understanding this psi r is actually thinking something of this form. So it's not a sandwich between two states with the same n, but between a state n and a state with n minus 1. Yes, because this guy is killing a particle. So this state n evolves in time with some given energy. Yes, so this is the stationary state with n particles. So this is n at time 0, this is the n at time t. And n minus 1, of course, it will be the same, but now with a slightly different energy with n minus 1 particle, n minus 1. So then you see that this guy here now evolves in time, which is nothing else than the psi 0, as I was telling to you. Evolves actually like E minus E, En minus En minus 1, T over H bar C0 of R0. So it does not evolve with the energy, but actually evolves with this energy difference, which is nothing else than the chemical potential. So the chemical potential, let me call you, this is the derivative of E with respect to the number of particles. This is the chemical potential. So this means that the stationary solution of the condensate, and I will come back to this point again in a second, actually evolves with an energy which is given not by the energy of the system, but by the chemical potential. Yes? We will employ this in a second. Yes. So this is because of how we define this, this condensate wave function as the mean field of the operator. Okay, so now we have introduced the idea of condensate wave function. We have seen how it evolves if it is a stationary solution. And we have also introduced the important idea that the condensate wave function has both an amplitude and a phase. Now we are going to derive the key equation that describes this condensate wave function. Yes, and which is going to be the so-called Gross-Pitayevsky equation. And the idea is very simple. We just start with the quantum Hamiltonian. Yes, so we start with this Hamiltonian that we already wrote yesterday. But now we will add the trap. Yes, we had some external potential, which is going to be the trap that the atoms experience. We have the kinetic energy, the trap, and we will have the interactions as well. This we had already yesterday. So this is our quantum Hamiltonian. And now I will do the Heisenberg equation associated to this Hamiltonian. So I will do the Heisenberg equation for the field operator. Yes. And this gives me an equation of this form. Yes, if you do the commutations, taking into account that these psi's are bosonic field operators, then you get to this equation. And now I will do the Bogoliubov approximation. So this means that I will substitute CRT by its mean, by psi 0 of RT. And then you see that the equation that this psi 0 has to fulfill is of this form. Okay, this equation is a very important equation for the theory of Bose-Einstein condensates. It's actually the key equation for the description of weakly interacting Bose gases at Bose-Einstein condensates at low temperatures. This is what is called the Gross-Pitayevsky equation. This Gross-Pitayevsky equation is nothing else than a nonlinear Schrödinger equation with a cubic nonlinearity. So this type of cubic nonlinearity in the sense that this goes like psi 0 square and psi 0 here. This gives you psi 0 to the power 3. So this is the nonlinear part, of course, this part of here. The rest is just the Schrödinger equation, right? These type of equations you find in nonlinear optics, right? In the so-called Kerr media. This equation, as I say, is the key equation to for the study of Bose-Einstein condensates at low temperatures. And actually, it works fantastically well for the description of experiments at sufficiently low temperatures, much more than the critical temperature. So, so this is the time-dependent version of the equation. For stationary states, you should use the time-independent version. And for the time-independent version, we just simply use which I just told you before. For stationary states, you should have something of this form with the chemical potential. Yes. So now, if you substitute this into the Gross-Pitayevsky equation, then you get simply this this thing. Okay. This is the time-independent version of the Gross-Pitayevsky equation. This is the equation that you use in order to find ground states. And you fix the chemical potential actually by normalization. You have to impose normalization. You impose that if you sum over all the condensate wave function density, then you will get the total number of particles in the system. And this fixes actually, at the end of the day, the chemical potential. We will see an example later on. Okay, so this, so we have now introduced the idea of condensate wave function, and we have derived the equations, which are nonlinear differential equations, that give us the condensate wave functions once we know the interactions and once we know the external potential that confines them. In principle, this equation is valid for attractive and for repulsive interactions, so for G positive and for G negative. From now on, I will discuss just G positive, yes. And at the end of this lecture, if I have time, I will discuss what happens with G negative, right? But let's discuss just the case of G positive for the moment. Okay, as I say, the condensate wave function is a complex number. So this means that I can write this condensate wave function as an amplitude, which I can write as the square root of the density. This is going to be the density n, right? Now, for a uniform condensate, n was a constant. Now n is going to be something that depends on space and in principle also on time. And then we have this phase ESRT. Okay, let's now substitute this expression here into the Gross-Pitayevsky equation, right? And then I will obtain two equations, one for n and one for the phase, okay? So let's see which is the first equation. The first equation that one gets is an equation for the density. And this equation acquires a very familiar form. Yes, I will not do all the steps. I just write you the result. You can check that this is correct. Yes, this is nothing else than the continuity equation. Yes, this has the form of a continuity equation. And this J is nothing else than the probability current. Yes, so the continuity equation, is nothing else than just the conservation of the number of particles in the system, right? The second equation that one gets there, one gets an equation for the phase, but I will actually not write the equation for the phase, but the equation for the velocity. Let me introduce this velocity here, which is nothing less than the gradient of the phase, and which is actually the velocity of the condensate flow. The velocity of the condensate flow. I will come back to the issue of this velocity because this velocity actually, and the fact that is actually directly related with the gradient of the phase, it's a very important issue. But I will come back to this point later on when we discuss the relation between condensate and superfluidity. So then I can write the corresponding equation for this velocity field, this Vs, which is minus the gradient of all these things that you have here. Okay, so I have this equation, which is the continuity equation, and then I have this equation for the velocity field, the velocity of the condensate flow, yes, which is of this form. Before going further with this equation here, let's have a look in these two equations where quantum mechanics actually is. Because these equations are almost completely classical, yes. The only place where you have quantum mechanics, where you have h bar, is in here, in this last term of the last equation. Yes, this term is the so-called quantum pressure. Quantum pressure. Yes. And this is the only term that contains actually the quantum character in here. Yes. Let's try to assess now how relevant, or rather irrelevant, this term is, right? So I am going to estimate, roughly speaking, this term. Let's have a look to this term that you have there in the quantum pressure. So this term, roughly speaking, is of the order, this is not a rigorous calculation, this is just an estimation of the order of how this is of the order of the inverse square of the typical length characterizing the density variation. So if my density is variating, yes, if it has some given length scale at which this variation is significant, yes, which I will call R, yes, this is the R is the length of, typical length of characterizing density variation. The typical length characterizing density variations. Yes, you see it from here. I mean, roughly speaking, what I did here in this estimation is that basically this nabla quadrat has units of 1 divided by length squared, right? Yeah, so this is basically how I did this estimation. So then this means that this quantum pressure I can estimate as something of the form h squared 2m r squared, roughly speaking. Now, if this number h bar squared divided by 2m r squared is much smaller than this other term, which is here, which is the interactions. So if you want the kinetic energy associated with this variation of the wave function is much smaller than the interaction energy, then this means that I can actually neglect the quantum pressure in this equation because it actually gives me very little contribution. Yes. And this regime, yes, is the so-called Thomas Fermi limit. We will see later on with an example what this means in practice, so to say, with a much better estimation, yes. But this is so-called Thomas Fermi limit. And in the Thomas Fermi limit, as I say, you remove the effect of quantum pressure. And this means that you recover a very simple equation now, which is this one. You have some external potential and G tensor. This is your equation. And this equation of here is the so-called Euler equation in hydrodynamics, the Euler equation of hydrodynamics, classical hydrodynamics, right? You have the Euler equation of hydrodynamics, yes, for a non-viscous gas with a pressure, which is the pressure in this gas is something like Gn squared divided by Ch. This plays the role of pressure in this problem. Yes. So this equation and the continuity equation, which we have here, yes, are the so-called hydrodynamic equations. So they are just purely classical equations. So we have substituted basically our quantum mechanical problem. We have done this sort of mean field approximation. So basically we have transformed operators into C numbers. And then we have removed basically all quantum mechanics from the problem and just reduced the problem to a classical problem of hydrodynamics. Yes, so these equations are actually very useful for the description of the systems within this Thomas Fermi limit that I was mentioning to you before. In particular, and this is particularly useful, if we are interested in the ground state, properties, in the ground state, Vs is 0, yes, so there is no flow. And this means that now we can just write this equation now as something of this form. So this means that Gn plus, which is a function of r, of course, Vx r is a constant. Yes. And now we can see very easily which constant is this actually, because if we have a look to the stationary equation here, then if you remove the kinetic energy, so if you remove this term of here, then you see that this, what is left here is the trap potential plus Gn, and this has to equal the chemical potential. So this is actually the constant that we have here. Yes. So this is actually the chemical potential. So this means that now, within this Thomas Fermi limit, we can easily obtain the density profile of the condensate. Is mu minus Vx r divided by G. Yes. So this means that we can easily obtain, as I say, the density profile of the condensate. And this is something actually very useful, right? For example, if you have an external potential, which is just a harmonic potential, which is the typical case, so something of this form, something like a trap in the x direction, a trap in the y direction, a trap in the z direction, so not necessarily isotropic, then you can easily see from this form that I have here, in this equation, that the density profile is actually something of the following form. right? And this N0 is nothing else than mu divided by G. And R, J, where J is X, Y, or Z square, is 2 mu divided by M and omega J squared. These are the so-called Thomas Fermi radii. Thomas Fermi radii that I have in this problem. So, as a matter of fact, what this means is that if my trap is a harmonic oscillator, yes, my condensate will have a shape which is just an inverted parabola. So if the trap is a harmonic oscillator, a parabola, the condensate is an inverted parabola, as you can see from here, because of this minus sign. Yes, it's something like this. Yes. In one of the directions, let's say in the X direction, it will be an inverted parabola with a given radius. The actual solution within the Thomas Fermi limit is actually very, very good, except at this border where you don't have this sharp boundary, but you have rather something like a border, right? So except at the very border of the condensate, the rest is fantastically well reproduced if you are within the Thomas Fermi radius. So let's see more clearly what is the Thomas Fermi limit. Sorry. So if now we impose normalization, so if you impose, as I was telling to you before, this condition, yes, now you can easily find what the chemical potential is. And the chemical potential is actually something of this form. You can do the math. And this omega is the geometric average of the frequencies. And LH0 is the harmonic oscillator length associated with this frequency omega bar. Now, the Thomas Fermi radius are, which I told you that is defined in this way. I can find it now that, let's say, a sort of average one with respect to this frequency omega bar square. So this is the Thomas Fermi radius. And this actually plays now the role of the typical length at which the density varies. Yes, so this is the typical length at which the density varies. So it's basically this R that we introduce here in this discussion. So now if you impose the condition that we were mentioning before for the Thomas Fermi, for this one, the Thomas Fermi limit, then you obtain the following condition for the Thomas Fermi limit. Yes, so this means LH0 comes from the trap. Yes, this is the harmonic oscillator length of the trap. A is the interaction, right? And this is the number of particles. So this means this formula is telling to us that if the interaction energy is sufficiently large with respect to the trap energy, you have the Thomas Fermi regime. For typical experiments, this is fulfilled, but it's not always fulfilled, right? So it's not always the case that experiments are in the Thomas Fermi regime, but many, many times they are indeed in the Thomas Fermi regime, if the number, especially if the number of particles is sufficiently large. Okay, so now we have introduced not only the condensate wave function and the equation that describes the condensate wave function, but we have also found these sort of classical equations, right? That that give me in a relatively simple way a very good estimation, actually a very, very good approximation within the Thomas Fermi limit of the condensate. Especially for a harmonic trap, this is particularly simple. Okay, so now that we have seen this condensate wave function, I would like to discuss very briefly something which is important, which is the relation between the condensate phase and the idea of superfluidity. Okay, I just told you that the condensate wave function psi r is something like the square root of the density and a phase. Yes, and so it's a complex number, and actually this phase is actually very important because it's what establishes the connection between superfluidity and the idea of BEC, the idea of Bose-Einstein condensation. And here we will proceed similarly to our discussion when we were discussing the Landau criterion. So let's consider first a reference frame in which the BEC is at rest. Yes, the BEC is at rest. So this case we have already discussed. You have something of this form. Yes, this is this stationary solution that we discussed before. You have some evolution, but it's a very simple evolution given by the chemical potential in the phase here. Yes. Now we will pass to a lab frame in which there is a motion, a fluid motion with velocity v. Yes. So then I can do the Galilean transformation here, and then I will get something like this. Instead of having here the chemical potential, I will have the chemical potential plus the mass of the fluid v squared divided by 2. Yes. But then I have a term, an extra term here, which goes like this, which is related with this Doppler shift that we were discussing yesterday for the Landau criterion. And this I can write now as a density and a phase. Now, and the phase is now time dependent. But now you see that S and V are directly related, because V, which is the velocity of the flow, the velocity of the superfluid flow that we will have here, it is just h bar m and the gradient of the phase. So, and recall that this is actually the flow velocity we got from the hydrodynamic equations, right? So the superfluid velocity is this condensate flow velocity that we were discussing before. This is the superfluid velocity. That we had before. So the superfluid velocity is related with this condensate flow velocity that we were related. It's actually the condensate flow velocity that we discussed before. And note that in deriving this result, we just assumed that there is a classical field, psi 0, yes, which is associated to the macroscopic component of the field operator. So basically, as I recall you, psi 0 is nothing else than this expected value of the field operator. So then we say, associated with the field operator, that this expected value, this macroscopic component of the field operator, which we assume that is something which is complex and has a phase. Now, if I now move to the lab frame, I get this this relation between the velocity and the phase, right? And then we have identified this V. This V is the superfluid velocity that we discussed yesterday. So we have identified then a direct relation between the phase of the condensate and the superfluid velocity. So there is a key relation between BEC and superfluidity, and it goes through the phase. But, and this is a very important point that I would like to stress, the relation goes through the phase. It is not true that the modulus, this square root of n0, I mean, the modulus, the n0, basically. So the condensate fraction, the condensate population, is the same as the superfluid fraction in the system, which is this rho s that I was discussing at the very end yesterday. So it's not the same that there is a one-to-one correspondence between condensate fraction and superfluid fraction. For example, and this we have seen already, At 0 temperature, an interacting Bose gas is not completely condensed. There is this quantum depletion that we discussed yesterday. But it is 100% superfluid at 0 temperature, this one can show. It is even more spectacular in the case of helium, for example, where the depletion is actually very, very large. In helium, for example, the condensate fraction is 10%, but the superfluidity is 100% at 0 temperature. So basically, the superfluid fraction is not the condensate fraction. But superfluidity is directly related with the idea of condensation through the phase, through the fact that the condensate has a phase. Okay, so let's stop here, and then let's see if there are some questions, and then we go on.
Hello.
Yes.
I had a question regarding just this comment you made.
Yeah.
Yeah. So you said at t goes to 0, we have total superfluid. The system becomes totally superfluid, but it's not a total condensate because there is some quantum depletion, right?
Yeah.
Yeah, but that quantum depletion is itself a result of changing in the Hilbert space because of the perturbation, right? So it is still in a ground state.
What do you mean by changing of the Hilbert space?
It is still in the ground state. All of the particles at t goes to 0. So why is it not a total condensate but slightly confused? Why stress on being n0 and not?
This is what we discussed yesterday.
Mm-hmm.
Yes. You remember what we discussed yesterday about quantum depletion?
Yes, yes.
So this is the discussion we had yesterday. So I showed you yesterday that there is always some part due to the quantum fluctuations of the excitations on top of the condensate.
Which is not in the t equal to 0 state, right?
This is at t equal to 0, yes. At t equal to 0, you have some contribution, some part, some quantum population, so to say, of excitations. There is a quantum depletion. And this is actually coming from interactions, as we discussed yesterday.
So my confusion lies in the point that this population, what we have, is still in the ground state of the system, right? It may not be t equal to 0 state.
Yes, but the ground state of the system, doesn't mean that you are condensed that all your particles are condensed in a single wave function, so to say. Yes, you may have, for example, that your ground state, and this we will see, for example, when we have a very strong interacting system, you may have that your ground state has nothing to do with a condensate. Yes, so we will see that, for example, I introduced before the idea of a natural state, and I told you that the ground state of a condensate is given when you have one of these natural states which is macroscopically populated. Yes.
Right.
Without any interactions, this state at 0 temperature will be 100% populated, and the others will not be populated. Right. But if I have strong interactions, then I don't have even the idea of a single natural state which is just populated.
No, but as you said, one body density matrix is there. So the eigenstate of the one body density matrix with the lowest energy, with the highest occupation, won't it correspond to the new ground state?
But if you diagonalize the single particle density matrix, right? In for example, in a state where you have no condensate, for example, you may have that there are more than one natural state which is macroscopically populated. That's my.
I see. I understand now where my confusion lies actually. So my confusion is exactly in the point that you are stressing that condensate is when, like for example, a uniform system with no trap, the condensation is when there is p equal to 0 population. That is the condensate.
The condensate is when you populate one state. Yes, one single natural state. Exactly.
Yeah, but if at t goes to 0, even if there is some interaction in the system, it is still populating only one state, right?
No, it is actually, you have some quantum depletion. Yes, you have some residual population in other states which are not the p equals 0. This is what we discussed yesterday, right?
But
okay, let's think about it, and then
I will think about it.
Okay?
Yeah, sure.
Okay. Yeah.
Okay, is there any other question? No. Then
Hello, I have a question.
Yeah. Continue.
So could you actually again explain the last part? So when you told that, and even though the condensate fraction is very low, that is not equal to the superfluid fraction. I don't understand exactly why this is the case and why this is happening.
Well, this is
the
because
reason?
I did not discuss in detail what the superfluid fraction is, right? Because I did not have the time to discuss it. But basically, this is what I was discussing yesterday about this two-fluid model. In the two-fluid model, you can take the mass density and you can write it as the composition of two parts, the superfluid fraction and the normal fraction. And this normal fraction actually decays as temperature, yes. If I remember correctly, it decays like T to the power 4 at low temperatures. So this actually means that at 0 temperature, this superfluid, this normal part goes to 0, and everything that remains is the superfluid. Yes. Now, as we discussed yesterday, the N0, on the contrary, is not exactly 100%. So this means that N0 is not exactly N at 0 temperature. When the system is strongly interacting, yes, then you may have that the superfluid fraction is 100% at low temperatures, or at 0 temperature, whereas the condensate fraction is much, much smaller. Yes, for example, in the case of helium. So it's not the same condensate fraction as superfluid fraction. But what is true is that the superfluid velocity is related with the gradient of the phase of the condensate. Yes. So it's important to have the condensate, but it is not the same superfluid fraction as condensate fraction. Okay.
So I have a question. So the quantum depletion you were talking about. So, but you said that for very high strong interaction kind of thing, the depletion is very large. But for that kind of strong interaction, the whole picture breaks down because we start from our
exactly.
Right. So then how can you say that means if that picture doesn't hold, then how can you say this?
My point, what I was mentioning yesterday, is that the fact that I am getting this quantum depletion means that when I start to increase more and more and more, then there is a point at which the whole picture breaks down, and then I need a different theory. This is absolutely true.
Okay. And another thing, the Thomas Fermi limit where you discuss the thing. So there you discuss two length scale, like means one is h squared 2m r squared and other is j. But there is another length scale associated with the temperature of the system, thermal de Broglie wavelength. So that doesn't have any role in this kind of.
Not in this discussion, because I am not considering the thermal effects here.
Okay.
I am considering very low temperature, but you are right. There is a third scale, which is the thermal de Broglie wavelength. Yeah.
Okay.
So one confusion regarding this. So when you're saying that you don't have 100% condensation because we have some quantum depletion, right? And that quantum depletion is because we have some phonon excitation in the BEC, right?
No.
And
no. It's not only because of phonons. It's just simply because of interactions.
Yeah, I mean, so I understood this from yesterday's talk that so this quantum depletion is actually it's because we are summing over VP square, and that part is coming from the phonons.
It's
right?
coming mostly from the phonons. Yes, this is true.
So if we have quantum depletion, that means that we have phonon excitation in the BEC, right? Can we?
Because you have interactions. It's because you have interactions. Not only phonons. It may be also rotons. But in this particular case, it's because of phonons. Yes.
Yeah. So when we have excitation, then how can we say that we have 100% superfluidity? I mean, because we have excitation.
This is because I did not do this calculation, so to say. But if you do the calculation of the normal part of the temperature of the, you have to take into account the excitations that you have on top of your condensate, right? Or for other systems, you have to take into account the excitations in the system, right? And then you have to integrate the effect of these excitations with respect to the Bose-Einstein population in terms of temperature, right? And then you will get the normal part. Yes, I cannot go into this theory in detail, Yes, but then you can see that the phonon part of the spectrum actually is contributing to, I think, with this t to the power 4. I don't have here the notes, but I think it goes with t to the power 4. And this means that at 0 temperature, it goes to 0. Yes. So there is a way of calculating this normal part. And as I say, this comes from the energies of these excitations and the Bose-Einstein statistics. Yes. There is a way of calculating.
Okay, thank you.
And
So
this,
there is another, yeah.
You go on.
Yeah, so there is another question from this that quantum part that quantum fluctuation we have this in the hydrodynamic equation. So for a uniform gas, we can safely say that this quantum fluctuation is 0, right?
This is 0. Yes, yeah. Because there is no curvature of the square root of the n, no?
Yeah, yeah. So, and now if let's say that we have a phase gradient because of some impurity that we excite in a PEC, then can we again say that this part will not come into picture, this quantum fluctuation, or it will be always 0, even with the phase gradient?
Well, it depends. As I say, you have to always to assess the importance of the quantum pressure, taking into account this criterion that I was mentioning to you before here in the Thomas Fermi limit, right? For example, if I introduce a perturbation in my condensate, which has a modulation which is relatively rough, so to say, so not a mild perturbation in this sense, right? But something which is much, in which the density variates much faster, so to say, in terms of space, not in terms of time, right? Then I should have I will have effects of the quantum pressure. Yes, this is. But I have always to assess the importance of this, right? Taking into account this here. Now, the important thing of why this quantum pressure is not important for the Thomas Fermi limit, you can see it from this shape. This shape is actually very flat in here. Yes, it's not like a Gaussian, which is like this, but something which is much flatter in here. This means that this curvature is very small, and this is why you can neglect actually. It's just as simple as that. Right?
I had a question. If you have a finite temperature system and rho n is non-zero, that means that there is some finite mixing of finite energy excitations. In that case, the occupancy of the zero momentum states in the finite energy excitations, will that contribute to N0? Or is it only the occupancy of zero momentum states in the zero energy part that contributes?
Well, the condensate is the condensate into the. I mean, you populate the condensate for a uniform system. It will be just the P equals 0, right? For the non-uniform system, it's something that you obtain from this expression of here. Now,
let's say. Sorry.
If you have.
Sorry, maybe I should clarify my question. So let's say I have a uniform system and it's a finite interaction system. So if I have zero temperature, then all of the system is in the condensate. Only rho s is
not all the system is in the condensate.
So the coherent state.
No, not all the system is in the condensate. If you are at zero temperature because of interaction, there is this quantum depletion that I was mentioning.
But it is in a coherent state.
If there is a temperature, no, not even that. Yes, you because coherent means this phase that I was telling to you, right? This is what coherence means in this case. So what you have here is that at zero temperature, there is some quantum population actually of these excitations. Now, if you are at finite temperature, what you will populate is thermally these excitations, right? So
yeah, so by coherent, I mean that it's in a single many-body wave function.
Yes, but the fact that you are in the single many-body wave function, this means that you are macroscopically populating one of these natural states. This is due to the discussion that we just had before, right?
Yes, and let's say at zero temperature there is a single many-body wave function which with a macroscopic.
No, this is precisely what I was mentioning to you. There is always some quantum depletion going out of the condensate. Now, if you are at finite temperature, then you will not only populate quantum mechanics, not only to have quantum fluctuations which populate these excitations, but you have also thermal population. And eventually, if your temperature increases further and further and further, then you will eventually destroy the condensate. Yes. Now, if you want to study this problem now at finite temperature, and the temperature is really something that you start to approach the critical temperature, then this Gross-Pitayevsky equation is not enough. You need to incorporate also the effect of the thermal cloud, the thermal excitations, yes, in a sort of self-consistent way. So, and this gives a much more complicated picture. So this picture of the Gross-Pitayevsky equation works well when the temperature is sufficiently low and when quantum fluctuations are not very large. So this means that you need to have sufficiently low temperature and with respect to TC, meaning, and you need to have that the quantum depletion is sufficiently small, right? Because otherwise the effect of quantum fluctuations will also kill the condensate. Yes. So your system cannot be very strongly interacting and cannot be very hot. Yes. It has to be cold and weakly interacting. This is the regime of validity of this formalism. Okay?
Okay, I think there is a question in the chat window.
One quick question I had, Professor. So the normal fluid part at slightly finite temperature, that will have contributions from quantum fluctuations and thermal fluctuations, right? Both can contribute.
I wouldn't like to enter into a very long discussion about this normal part, because since I didn't do the calculation here, yes, okay, then it will be very confusing, so to say, right? So okay. I think that we should skip this discussion, right?
Okay, Luis, probably last question in this section. Why it is called pressure in the quantum pressure? Okay, there's one student was asking.
Oh, because this part of here is adding to this part of here, and this part of here is this gn squared. You see, this part of here is the derivative of the pressure here. So this part of here is related directly with pressure. So this is why it's called quantum pressure. Yes, this is because of the this is the classical pressure that you will have here, and this is the quantum pressure. Okay, this is just coming because this is the Euler equation of hydrodynamics, and this acts like a pressure. Okay.
Okay. Okay.
So let's move now to the final discussion that I would like to make. So I would like just to discuss two things if I have time. So one is about the fact that we just discussed, which is the fact that the superfluid velocity, V, is directly related with the gradient of the phase. This means, of course, that the rho of the curl of the velocity field is 0. So this is what is called an irrotational flow. Yes, and the fact that the flow is irrotational in a superfluid has very important consequences for how these systems actually rotate. Yes, because it will be very different than the rotation of an ordinary liquid. An ordinary liquid rotates like basically like a rigid body. Yes, I will discuss this in a second. A superfluid cannot rotate in a similar way. Yes, but it is clear that if I take a superfluid and I begin to stir this superfluid, yes, then at some point this superfluid has to introduce rotation in some form. Yes. Yes. So if I have, let's say, a superfluid in the lab frame, and it has some given energy, and I have my superfluid, I have some axis here, and I start to rotate with some angular frequency, omega. Yes. Then if this is the energy of the system in the lab frame, and I move to the rotating frame, I will see that in the rotating frame I have something like this. Yes. So it is clear that, and this is the angular momentum, and this is the rotational frequency. Then it is clear that for a sufficiently large frequency, yes, this omega, then it is actually energetically favorable to have an angular momentum L different than 0. So I should introduce some angular momentum into the system. But how this can be done if the flow is in rotation? And the way out of this problem is actually to say that this flow is actually introducing the superfluid through the idea of a vortex line, which is a line which has 0 density in the vortex. It's a singularity, right? I pile up the curl of the velocity there. I pile up the vorticity there. But in here, there is no density, yes? And then, so this is the idea of vortex line. So if I start rotating my system, then at some point my system develops, for a given critical frequency of steering, so to say, my system develops these vortex lines, which are these singularities. Now, so if I have, let's say, if I am rotating around this axis, let's say the Z axis here, then at some point my system will develop, as I say, this vortex line, and it may develop more than one vortex lines, more than one vortex, 2 vortex, 3 vortex, and so on, for further and further rotational frequency. Now, the rotation, the velocity field of a superfluid around these vortex lines, right? This type of velocity field that we will have here in a superfluid, I will put Vs, so superfluid, is actually a kind of interesting object, yes? Because if I study what is called the circulation of the velocity field, the circulation of the velocity field. The circulation of the velocity field is something very simple. It's just, which I will call kappa, is the line integral around these closed trajectories here of the velocity field, yes, as I say, along these closed paths. But now this velocity field, as I say, is h bar m and the gradient of the phase. So this means that what we are having here is h bar m and the gradient of the phase times dl, which is nothing else than the phase that I pick up when I go around this trajectory, as when I go around the trajectory. But yes, this phase that I pick up when I go around the trajectory, I have to take into account that now, so if when I go around the trajectory, I start in a given point and I end in the same point, yes? So I start in this point and I end in this point, which is the same point. And at this point, I have a given wave function, CR. And this CR, this is the wave function of the condensate, has to be well defined, has to be uniquely defined, yes? And this is now a density times a phase, yes? And this phase has to be well defined. So this means that when I go around, if I pick up a phase, this phase has to be actually a multiple of 2 pi, 2 pi times n, some multiple of 2 pi. Because when I go around, if I pick up a phase, it has to be a multiple of 2 pi, because otherwise I will not have a unique wave function in the system. So this means that the circulation is actually quantized, it's something of this form. The circulation of the velocity field around a vortex in this superfluid, simply because I have this notion of having a phase, right? A well-defined phase, then up to, let's say, multiples of 2 pi, then the circulation has to be a multiple of 2 pi. And this has important consequences, yes? So if now I consider this vortex line as a straight line, it's not always the case, but let's suppose that this is a straight line, and this is the velocity field, Vs. Yes, this velocity field will be now, since this is cylindrically symmetric now, it just depends on rho, on this distance rho. And it goes in the phi direction. Yes, it just goes tangential here, the E phi direction. So if I calculate the circulation, dl, this is Vs rho, and the perimeter of this circle, which is 2 pi rho. So this is the circulation, and the circulation, as I say, it has to be a multiple of 2 pi n, 2 pi h bar m. So this means that the velocity field is actually of this form. So the velocity field is inversely proportional to the distance to the vortex line. Yes, you can make the math and then check that this is indeed 0. Yes, the velocity field here. So you take the curl of Vs, since this is just in the E phi direction. Yes, so this is in the E phi direction. It is of this form. And this is obviously 0 because rho times Vs is a constant, so this is 0. So this is indeed an irrotational flow. But now we have to compare this with a normal fluid. So this is for a superfluid. But what happens with a normal fluid? For a normal fluid, the situation is like in a rigid body. So V, the velocity field, and here you can just recall your analytical mechanics, is the velocity, the angular velocity cross r, yes, and of course now the curl is not 0, it is actually twice omega, yes. So this means that this velocity field is actually omega rho E phi. So this is the rigid result, right? So let's make just a plot. The rigid result. So if this is rho, the distance from the vortex line, the distance from the rotational axis, let's say, and the velocity field, right? For a rigid body, this goes like this. This is a linear function, omega times rho. Yes. But for a superfluid, it looks completely different. It goes like this. Like 1 over rho. It is completely different. Actually, the velocity field diverges close to the vortex line. And actually, the fact that it diverges close to the vortex line means that there the kinetic energy is infinitely large. And this is actually what prevents the particles to reach the singularity. This singularity, this vortex here, it is always coming together with a hole in the density. Yes, so there is always a hole in the density. So if you look at from the top here, you will see that the vortices actually look like a hole here. There is always a hole. There is this velocity field here going around this hole, but in there is no density. The singularity is, if you want, naked, in the sense that there is, the singularity is always at 0 density, right? And is there where we are piling up this rotation, this curl, actually, it's just singular there. But there is no density of superfluid in there. Yeah. Now, if you rotate faster and faster and faster, so as I say, there is a critical velocity at which, so you start rotating. So if this is the frequency of steering, for a critical frequency that is below a given critical frequency, there is no vortex. Then there is one vortex that enters. Then you will have, for further velocities, you will have 2 vortices, 3 vortices, and so on. And eventually, you will have what is called a vortex lattice. This has been observed, for example, in the case of condensates. Yes. And actually, you will start to have so many vortices that this system starts to behave, starts to mimic actually the rotation of a rigid body. Okay, so the important thing, as I say, in the case of superfluids, is that due to this irrotational character of the velocity field, the rotation is very different. And you will have this idea of vortex and vortex cores. This is what is called a core of a vortex. And these vortices are quantized. So this means that they enter one by one, and they start forming this type of vortex lattices. So this is one of the consequences of having a rotational character in the superfluid velocity. Another spectacular consequence of the irrotational character of the superfluid velocity is in the reduction of the momentum of inertia, of the moment of inertia. This I don't have time to discuss in detail. Yes, the moment of inertia. Yes. So you know that if you have a rigid body and then you start rotating around this, then there is a given relation between the angular momentum and the rotational frequency, which is given by the momentum of inertia. Yes, so if this rotates with some given frequency omega, then this gives you j times omega, and this is the moment of inertia. Now, this moment of inertia is something of the form mass times distance to the power 2. Well, this is this distance with some prefactors depending on the shape and so on. Now, in a super fluid, yes, if the superfluid is cylindrically symmetric with respect to the axis, right, then this momentum of inertia is exactly 0. Yes. If there is some anisotropy out of this cylindrical symmetry, then there is some residual moment of inertia. But if the moment of inertia, yes, but if the superfluid, if the BEC is perfectly cylindrically symmetric, then this moment of inertia goes exactly to 0 due to this irrotationally. I don't have time to discuss that, but this is one of the important consequences of the fact that the velocity flow is irrotation. Okay, so this is what I wanted to discuss about this irrotational character, which, as I say, is a direct consequence of the fact that the velocity, superfluid velocity, is directly related with the gradient of the phase of the condensate. And now, in the last minutes, I would like to come back to a question that was posed yesterday about what is the fate of a condensate when the interactions are attractive. Yes. So the BEC with attractive interaction, so with G negative. Yes. So in this case, so let's write the Gross-Pitesky equation that we would have. I will put it like this. So G is minus G. Yeah. Yes, so this is our Gross-Pitesky equation. And then you see that this part of the energy, right, which is given by the attractive interactions, you minimize this part of the energy by increasing the density. Now it has a minus sign. Yes, so the larger is the density, the more negative this part is, and therefore the smaller is the more negative is the energy. So this part of here tends to contract the condensate. Yes, tends to contract the condensate. Now, so this means that if I have a trap, yes, and I have a condensate with some given shape, right? This tends to contract. So this tends to do something like this. Tends to make it now contracted in this direction. Now, for a classical gas, this would be unstoppable. So what it means is that in a classical gas, in classical mechanics, the minimum of the energy is in here. The minimum of the trap energy of the harmonic oscillator is in there for a classical gas. Yes, and this means that both the classical energy of the harmonic oscillator and these interactions will be minimized by putting all the particles into the center, into the very, very, very center, and the system will eventually collapse. Yes. But quantum mechanically, the situation is different, because quantum mechanically, the harmonic oscillator, for example, has the minimum of the energy of the harmonic oscillator is not zero. It is given by the first state, yes, h bar omega half, let's say, of the harmonic oscillator, yes, which has some given width, yes. So quantum mechanically, you have some quantum mechanical dispersion associated with the 0-point oscillation of the system. Yes, you have some 0-point oscillation, some 0-point energy in the system. Yes, and this is quite important to understand why you can have at all Bose-Einstein condensates with negative scattering length, with attractive interactions in experiments. Because now you have this part of the Gross-Vitebsk equation, this part of the energy of the system, which is basically the kinetic energy in the trap, yes, which for a harmonic oscillator is the harmonic oscillator Hamiltonian, which is characterized by a 0-point oscillation. Yes, so this has a 0-point oscillation of the order of h bar omega, right? And this energy is independent. It's independent of the number of particles. It's a single particle energy that you have here. So this is single particle physics. This is independent of n, independent of the number of particles. So this is the 0-point oscillations. On the other hand, you have this part of here, yes, which tends to collapse. This tends to contract the BEC. But this part, of course, is proportional to the number of particles that we have in the system. Yes. So it's given by interactions and is proportional to the number of particles that we have in the system. So on one hand, we have this attraction, these attractive interactions which tend to gather particles in the center. And on the other hand, we have this single particle effect given by the 0-point oscillation, which is actually opposing this contraction. It's basically dispersing, pushing outwards. So you have this inwards and this outwards, yes? And now what happens is that, as I say, this part grows with n, and this part is independent of n. This means that there is so that you have a competition between them, but it's clear that if the number of particles is sufficiently large, then this part of here will, of course, dominate with respect to this part of here, and then there is no way of stopping the collapse. But if the number of particles is small enough, yes, then you can actually stop the collapse and get a stable, or at least a metastable solution. In order to see this, one can do something very simple, which is just doing the following. Yes, we will do an ansatz, yes, which is of the following form. I will skip here all the factors. It's basically a Gaussian ansatz. Yes, I take a Gaussian ansatz for the wave function of the condensate, which I will write like this, right? This H0 is the harmonic oscillator length, and this lambda is a variational parameter. Yes. There are here some prefactors for normalization and so on, which I will not discuss. Now I can calculate the energy in my system, and the energy has the contribution of the kinetic energy, the trap energy, so it has all these contributions, the kinetic energy, the trap energy, and the interaction energy. So if now you plug this into so basically this energies of this form, it has the kinetic energy, you have the trap energy, and you have the minus g divided by 2 and psi to the power 4. Yes. So if you plug now these variational ansatz into here, then you get something of the following form. Okay. Let's see the different ingredients. This is the kinetic energy. The kinetic energy is always proportional to the inverse of the length in the square. Yes, this is why there is 1 over lambda squared. This is the trap energy, which depends like length in the square, because this is the parabolic dependence of the harmonic oscillator. And then this is the interaction energy. Interaction energy in 3 dimensions depends like 1 over length to the power 3. So this is density, right? But in d dimensions, you will actually scale like 1 over length to the power d, which is the density in d dimensions. Yes. Let's see why I say this in a second. Okay, so if now you plot this energy functional as a function of lambda for different values of n, you see that this is the proper number here, which incidentally you should remember it is what we were having before for the Thomas Fermi profile, for the Thomas Fermi limit. So if we plot now E lambda as a function of lambda for different values of the number of particles, then you get always some things, some curves of the following form. Okay, so this is for a given number of particles, N1, N2, N3, and so on, where N1 is actually smaller than N2, smaller than N3, and so on. Okay, so you see what we are having here. In this part of here, this is just the effect of having a trap. This is just this lambda square that is going up. This is the trap. In this part of here, we are dominated by the 1 over lambda cube, actually. So this is this lambda square. This is 1 over lambda cube of the interactions. But you see that here, there is the possibility of having a minimum. Yes? So there is a possibility of having a condensate with a finite density, with a finite width. Yes? If you go to this regime here, then there is no way of stopping the collapse. Basically, your system will just minimize energy without limits and go to an infinitely large density. Of course, before this happens, then you will have a lot of other things going on in the system. Yes. So, and the trap is of course very important, because without trap, this will actually look like this. Yes. So without trap, which is actually doing you like this, without trap, your system will either expand without limits or contract without limits. Yes. So the answer to the question of yesterday, whether there are condensates with negative scattering length, the answer is yes. At least it's a very highly metastable state. Because you can prevent the collapse for a sufficiently small number of particles because of the presence of this barrier here. And this comes directly from the quantum zero-point oscillations in the trap. But if the number of particles is too large, then it just simply crashes and gets a collapse. If there is no trap, then there is no condensate either, because either the system expands without limits and therefore it gets completely diluted, or it just collapses and gives you infinite density. This is in 3 dimensions. In 1 dimension, yes, in 1 dimension, the situation is different, because in 1 dimension, we should have a look to this. In 1 dimension, you have that the kinetic energy is always proportional to the density in the square, to the inverse of the length in the square, whereas the interaction energy, it goes like 1 over length to the power of the dimensions, which is 1. So I am now talking about 1 dimension. So now let's try to make the same graph now without, we don't need that to have a trap here. And then you see that for large values of L, of course, this interaction is negative now. For large values of L, this part dominates, yes? This is the part that dominates, and this is negative. It is here. Yes, and it decays like 1 over L. For small values of L, this part of here dominates, and this is positive. So this means that we are here going up and diverging. So this means that at some point the system actually makes something like this. Yes. So this means that in 1 dimension, contrary to 2 dimensions or 3 dimensions actually, you may have the possibility to have a condensate at a finite density. Yes. And this is actually related with the idea that in one-dimensional systems, if you take this type of nonlinear Schrödinger equation that we were discussing from the very beginning, the Sklodowski equation, yes, you take this equation in 1 dimension, it is well known that this equation has something, solutions which are called solitons, soliton solutions, yes, which are typical of these nonlinear Schrödinger equations in 1 dimension, right? This here is very much related with this idea. In 1 dimension, you don't have collapse, but rather the formation of this type of self-bound solution. You don't need a trap, yes, which are called solitons. And actually, indeed, the physics of solitons has attracted a lot of interest in the BEC community, and one has observed actually these solitons in experiments. Okay, so this is all I wanted to say about BEC. So I did not comment anything about excitations, very little about nonlinear physics and so on. I did not mention anything about interacting Fermi gases, weakly interacting Fermi gases, because this will take me also quite long. But I hope that you have gotten at least a broad idea of the main ingredients for the BEC physics. And then in the next lectures, we will pass to something quite different, because in this very different world of these strongly interacting systems, basically you cannot employ all these ideas, because there the depletion is very, very big. So to say, you cannot even talk about the condensate. Okay, so but this we will see in the last 2 lectures. Okay, thank you.
Okay, so now we again open for questions, and please go ahead, ask me.
I have a question. So in the section where you solve the harmonic oscillator, harmonic potential problem, what happens when X is larger than Rx? Why does set N appear to be negative?
Sorry, once more?
In the solution to the harmonic potential, the Thomas Fermi solution to the harmonic, yes, that one. So when at large values of X, N can go negative, what does that actually mean?
Well, that's correct, because what, as I told you here when I tried to make this plot, this solution is only valid within this radius, so to say, within these boundaries. Yes, starting close to the boundaries, right? The actual solution is actually different, and it's never becoming negative, of course. Yes. So this is
an artifact of some approximation.
This is the artifact of the approximation, because the approximation breaks actually down in here.
Which approximation breaks there?
It breaks down this approximation, the Thomas Fermi approximation.
I see.
Because you see, at this point the density is just simply small. Yes, and then this is small, and then you break the Thomas Fermi limit. So the Thomas Fermi limit is good in this inner region, yes, but at the border, close to the border, it becomes to be wrong, yes. And definitely, of course, the wave function can never become, the density profile can never become negative.
Thank you.
Luis, there is one comment, like, is it fair to say that the quantum pressure prevents collapse in an attractive condensate?
Yes, this is absolutely true. It's the quantum pressure actually which prevents the collapse.
Yeah. And the second question, elaborate a bit more on how the multiple vortices are showing up at large omega values.
Well, it just simply enters basically one by one. Yes, so I did not have time to comment on that because this will again bring me very far away from where I want to go. But if the first question, which is interesting, is actually how a vortex actually, a single vortex actually enters. And how this happens is not so trivial, right? Because it happens actually through the following reason. You have a condensate, and I am looking now from the top, no? So now the system is, I am steering the system like that, from the top. And now what happens, as I say, vorticity is quantized. The circulation is quantized. So you can understand this as a charge. I cannot have half a charge in my system. Yes, my charge, I have to bring actually a charge from outside into my system, right? Yes, I cannot have half of this charge. They go one by one. You can understand it as a charge, yes, which has to be quantized. So what happens is that I have to enter a vortex from outside. And this is done by the following way. The surface of your BEC, yes, the surface of the BEC actually becomes unstable. One has the so-called surface modes, which become unstable. So you get some modes of this form, like this. I don't know, something like that, yes. You get this surface mode, and now I am exaggerating. And then associated with these perturbations here, there is the formation of vortices here at the border, yes. Now, what happens is that due to this destabilization of the vortex, right, one of these vortices enters inside, yes, and it goes to the center because it's there where it eventually minimizes the energy. So there is a combination of dynamical and thermodynamical instability here. And then eventually you get a vortex in there. Now, due to the same mechanism, more and more vortices will enter when you start to have more and more rotation, yes. And eventually you build actually a triangular lattice of vortices, which is called Abrikosov lattice, right? And this type of Abrikosov lattice, so basically you get a triangular, because this is what minimizes the vortex-vortex interactions. I will not enter into that. And then you get more and more and more and more and more and more. And eventually you can describe the system basically like a continuum of vortices, and then you eventually can recover a rotation which looks very much like the rotation of a rigid body. So this is the way a vortex enters in a system, and more vortices enter.
Okay. So is there any other question you can ask directly?
Yes. So I have a question. So about the vortex thing, vorticity you discussed there. So there you don't mention the dimension part, right? Which dimension you are considering. But this kind of vorticity kind of concept, like it's a topological invariant, and this concept only holds for two-dimensional system, right?
Two-dimensional or three-dimensional?
Or even for three-dimension it also holds, but then the defect is like vortex or some kind of other thing in 3D.
In 3D you have vortex lines, right? So basically you have this vortex line.
Oh, okay, cylindrical thing. Okay.
But it is true that then you have more degrees of freedom, because for example you have the modes of this vortex, right?
Okay.
And eventually these vortex lines could even form vortex rings, right? Which everybody is very familiar from the smoking vortex rings, basically, that you get when you play with the smoke, basically, right? You get these vortex rings here. So you have more possibilities. You may have vortex reconnections, and even you may have you may study turbulence in this type of systems. So there is people who is, and actually there's people who is studying this turbulence in experiment.
Okay. And so means 2D vortex kind of thing is possible, means with this kind of trapped potential in 2D also Bose-Einstein condensation is possible, because with that kind of dispersion P squared by 2m and without a trap. Yeah, right.
But what I told you yesterday about the physics in 2D and in 1D is that in some sense these experiments have some finite size, right? And
Okay.
and due to this,
you cannot see the decay, that part you discussed.
Exactly.
Okay.
But if you make your system bigger and bigger and bigger, eventually you will see strong phase fluctuations in your system, which mean that you don't have actually a condensate. Yeah.
Okay, right. Okay. And the off-diagonal long-range order, why it's called the off-diagonal long-range? I understand that it's n0 after means asymptotic value, it's going to some constant. But the off-diagonal means what?
Off-diagonal is because you get R and R prime different than each other. Because if you have, you may have also an order associated with the density. Yes. When you have, for example, a crystalline order, right? This is what called diagonal long-range order.
Okay. Thank you. Okay.
Now, an interesting thing, which is now something quite active, is the possibility that you may have actually both order parameters at the same time. So basically, you can have a diagonal long-range order and an off-diagonal long-range order. Diagonal long-range order is associated with crystalline structure. So basically, instead of having a condensate which is flat, you have a condensate which is like this in density. And then this part is associated with superfluidity, as I say. So this means that you may have something which is at the same time a crystal and at the same time a superfluid. This is what is called a supersolid, which is something which is kind of very active field now in the context of experiments in what is called dipolar Bose-Einstein condensates.
I had a question.
Yes.
Regarding off-diagonal long-range order. So as you said, if we have an external trap, like you put a simple harmonic oscillator, so is there again a similar notion to off-diagonal long-range order in such systems?
Well, as I was commenting, the fact that you have some finite density, some finite size, yes, it's not only just the homogeneous trapping, it's the fact that you have a finite size. Yes?
Right.
And this means that you don't let this decay go far. So if you could see your system for very big distances, then you could see actually this decay. But if you are just cutting off here, yes, then basically you can mimic the equivalent of having a off-diagonal long-range order.
Right.
And then it happens something interesting. Yeah, you can be in one dimension. You don't see these strong phase fluctuations actually, which will happen if your system is sufficiently big. Yes, but this means that if you make your system bigger and bigger and bigger, at some point you will see these phase fluctuations popping up. Yeah.
No, okay, thanks.
Luis, two questions, but I will summarize that two questions regarding vortex. What is the charge of vortex? And combining these two questions, it just means that by rotating, do you create simultaneously both vortex and anti-vortex, or just one circulation like vortex?
You can. So first of all, about the charge. The charge is this number n here. Yes. This is the charge, right? This. So this is the charge. As Rejish was mentioning, you can have a vortex, let's say in this direction, or an anti-vortex in the opposite direction, right? Now, when you steer your system, yes, you are choosing a particular direction, so you will bring vortices in a particular direction. But that said, if you, for example, perturb your system in a strong way, right? For example, suppose that you have a condensate and now you pass a defect here. This is a defect, and you pass it very quickly. Then what happens is that you introduce vorticity here at the borders. So basically, what this is actually done in experiments. You take a BEC and you take a laser, yes, which is like acting like a barrier, and then you drag the laser across the BEC. And then what you observe is actually along the path of the laser. So basically, the laser just did like that. You start to see the formation of vortices, right? And there you may have vortex and anti-vortex, indeed. Vortex and anti-vortex, they have charges which are positive and negative. So they are like positive and negative charges. So in principle, in presence of dissipation, they may actually go towards each other and cancel each other. They can kill each other. Yes, this cannot be true with positive and positive, because otherwise you will not conserve the charge, or negative and negative. Yes, actually, vortices act in some sense similar to charge particles in electrodynamics.
Okay, it's probably so last. I think that is you always get a precursive lattice, or it can be just a random arrangement of vortices.
Well, if you allow the system to go to the lowest energy configuration, the minimal energy configuration is given by this triangular lattice. Is what minimizes the vortex-vortex interaction. It's a so-called precursive lattice.
So I think there is a naive question. What is the reason only bosons can condensate? It is only because there is no equivalent Pauli exclusion principle for bosons. Like, what is so fundamentally different about bosons? I think.
Well, bosons follow the Bose-Einstein statistics, right? This is what we discussed yesterday.
Okay, so is there any other question?
So I have another question. So here the kind of potential means kind of potential between the particles we have considered. It's kind of short range kind of potential. Right? So if we instead of that we use some long range kind of potential, then we can expect this kind of superfluidity, or the phase kind of is very different from the like normal to superfluid kind of transition is very different in long range kind of potential.
If the interactions are not contact, and there are cases in which the interactions are not contact, for example, you may have, for example, that the particles interact via dipole-dipole interactions, for example, because they are like magnetic dipoles or electric dipoles. So they interact like something like 1 over r to the power 3, and then there is some dependence like that, like in the dipole-dipole interaction. Then in that case, you may have, again, a Bose-Einstein condensate, you may have supersolid, a superfluid, and as I say, also a supersolid. Actually, these supersolids are studied in this context.
Okay.
But by changing the interactions, you change to a very large extent the rules of the game. Yes. So there are many, many properties. And actually our group, for example, and also Rejish group, we are very interested in this because basically by changing the interactions, since I was commenting yesterday that interactions play a very important role in the properties of these systems. So if you change the nature of the interactions, you change very much the qualitative properties in this system, not only quantitative, but qualitative properties.
Okay.
I have a question. So when you're saying like you can create vortices and anti-vortices by moving a laser through these, so do we need any specific condition on the laser that we are applying, or is it true for any impurity that moves inside?
If it is something very, very narrow, yes, then, and the velocity is smaller than the critical superfluid velocity, in principle, I should not create excitations in my system, right? This is the idea of the Landau criterion that I was mentioning yesterday. Yeah, but if I drag my system, and typically this is how it is done, so you cannot drag it with a needle, basically, you have always some size, then you indeed actually induce this vorticity. And if you shake your system very strongly or you do other things, then you can induce indeed turbulence in the system. So you get cascading of vortices and things like that, like in turbulence. And as I said, this sort of quantum turbulence is something which is very interesting and something that people is studying.
Okay. So what I understood, like when you have an impurity.
Louis, probably a last question.
Yeah.
So how is it possible to? Oh, sorry.
Okay.
Yes.
Can I say? Yeah. So what I was actually saying is that so as we have, let's say, some normal impurity in the PEC, like we have sometimes split work impurity in the PEC, right? So in that case, we are already exciting some phonons. Like, I mean, we are creating like some part of the condensate with uncondensation. So in that case, so we cannot expect to create vortices and anti-vortices, right?
I didn't understand the question. Sorry.
So what I'm saying is like,
So,
let's say we have
yeah.
Sorry.
Sorry.
Yeah. So what I'm saying that so it depends on the basically the strength of interaction between the impurity or the laser that we are applying with the condensate part, right?
Well,
Either the
Rejish? Hello? Okay. So what I mean is that...
Yeah, I think his voice is breaking. Can you hear me? Hello?
Hello?
Luis, can you hear me?
Yes, I hear you.
Okay. So probably what he means, like when you move that laser through the condensate, it creates phonons, and then how is it like vortices are created?
Yes, when you move, you can create this. As I say, if you move sufficiently fast, yes, eventually you start creating excitations, right? And if you do this with, let's say, with a needle, basically, then for a velocity smaller than a critical superfluid velocity, you should not create excitations. But if you drag sufficiently quickly, then you create excitations, and then you start to heat up your system, right? Now, depending on how do you do it, then you can create phonons, right? In other systems, you will create protons. But if you do this, as I say, with this broader barriers, then you start creating, you start affecting more strongly your system and creating vortex anti-vortex pairs.
So what I'm actually trying to say that even without moving a laser, if let's say that we have sufficient interaction between the laser or the impurity with the condensate, so even at the static position, we can create a large number of phonons, right? I mean,
no. Well, if the impurity is not moving, then it happens the following. This is an interesting point, actually. If suppose that you have a condensate and you put an impurity, like a barrier here, yes? So you have a barrier and here you cannot penetrate. Then what happens with the condensate? Here the density has to be 0. Here the density has to be some uniform value, yes? So there is a sort of a skin here at which this goes from being a constant value to being something like 0. This distance of here is the so-called healing length in the system. And the healing length is very easy to find. Is basically this energy is equal to Gn. So basically is then the length associated to this energy scale, Gn, where n is this number in here. So this means that if you put a barrier and this barrier is not moving, basically what you have, let's put a condensate, let's put this impenetrable barrier here, then this means that there is some core region here around, and this is actually incidentally what happens in a vortex core, at which the density goes eventually to 0. So this is this region that I am plotting here, yes. And outside of there, the condensate is basically unaffected by the presence of this region. So you are not. So if you are in the stationary state, so basically you don't have anything else than that. Okay.
Okay, Sandra, you want to ask the question directly? There is one student, my student actually. Sandra?
Yeah, sir, I have this doubt that how we are managing to condense alkali atoms or atoms which are actually made out of fermions but as bosons in actual experiments that we do.
Sorry, once more?
How are we able to condense the atoms which are made out of fermions like protons and neutrons and electrons in
Well, because
the actual experiments that we do?
Well, because you composite so basically your oops. Hello. So basically you are not proving this physics at this very high energy, right? So your system is, you are just simply seeing the composite of the two, yes, and this composite is a boson, yes. You are not proving the physics at this very high energies for having a proton or an electron. You are seeing this as a single particle, which is a boson. Yes, this is a simple as that. Yes.
Oh.
Now, other thing which is interesting is that if you have a Fermi gas, which I was not discussing, right, you may actually form you may actually gather fermions together. So two fermions, pair these two fermions together. If you pair them very strongly, let's say in a molecule, this, and you are not able to prove the energy associated with this binding energy, which is very high, then you can get a condensate of molecules, right? But you may have a more subtle way of pairing them, which is the so-called BCS-like pairing, which is directly related with low temperature, at least superconductivity, which is the fact that you can get a pair. This pair is actually not in space, but is a pair actually in momentum. And these pairs somehow, it's not exactly the same, but somehow condensed, right? And they give you this a sort of superfluid of pairs now, of these pairs, which are now acting like boson. And this is basically, this superfluid of pairs is actually the reason of this superconductivity. Yes. So you can have also a superfluid of fermions, right? But understood in this way, either because they pair locally, like a molecule, or because they pair in momentum, like these superconductors. Okay.
Okay, I think if there is no other question, let's thank Luis again.
Thank you. So as I say, in the next lecture, I will start with atoms in optical lattices. So I will start discussing a little bit about pieces in optical lattices, but then I will move quickly to strongly interacting systems. Okay. Good.
Thanks, Luis. Thanks, Luis. So see you on Monday. Okay.
Happy Easter. Ciao.
Yeah. Happy Easter. Yeah.
Ciao.
Ciao.